So in this optimization problem, we are trying to find require the shape to have a total of 216 square feet and minimize the amount of fencing required. So the first thing you need to do is label the shape with variables. I like to give the distance that's repeated the most the variable x. So there are 3 vertical lengths in this figure and 2 horizontal, and so I'm going to label them this way. That's fairly arbitrary, but it'll be easiest if we do it the same way. So then we know that the total area is 216 square feet. So that means I'm going to write that down as an equation. Area is 216. Now, any formula to find the area of the rectangle would be a good idea. But I'm going to go ahead and just write it with x and y because that's the variables here. So area is x times y, the total area of this shape. So we know that the area in this problem is constrained to be 216. X times y must be 216, and we will need to have this variable y isolated to help us in the rest of the problem. So I'm going to do that now. Now, what we're trying to minimize is fencing. So we want to find the minimum fencing that meets the constraint of fencing is equal to all of these sides added together. So in that figure there are 3 x's plus 2 y's, and fencing as a function of x is going to be 3 x's plus 2 times whatever y is, and y is 216 over x. So this is the function that we want to find the minimum of. I'm going to clean it up a little. 3x and 2 times 216 is 432 divided by x. Okay, so basically all that's left to do is to graph this function on a graphing calculator and to find the minimum of it. That sounds easy, but the hardest part about that sometimes is finding a good window to graph this on. So if you are going to multiply 2 numbers, x times y, and have the area be 216, we want to just take a guess, get some kind of reasonable answer for this, knowing that the area has to be 216. So I'm not going to guess a number like 1 for the side length of the fence, because then this side would be 1 long and y would have to be 216 long. It doesn't make any sense for this problem. And 5 is probably too small as well, because 5 times, let's see, 216 divided by 5, it would be, if x were 5, then y would have to be in the 40s for us to get 216. So 10, I think, is a good place to start for this. If x is 10, then y is 216 divided by 10. So that's a good one because it's easy to calculate what y is. It would have to be 21.6. And then you want to see what the fencing is like. If this side is 10 long and this side is 21 long, then how much fencing would that be? 10 plus 10 plus 10 plus 21.6 plus, I'm going to get that number with the calculator. So that will be 3 times 10 plus 2 times 21.6, which is 73.2. Now, I'm not sure that that's such a great guess, so I'm going to go ahead and put in 20 and see where we are with that one. 216 divided by 20 to get the y variable and then this is 10.8. So then we have 3 times 20 plus 2 times 10.8, and that is 63.2. This is a 10. Alright, so by doing that, then I have a reasonable idea of how to scale this graph that I'm going to use the graphing calculator for. So on this graph, I'm going to be graphing the function that represents fencing as a function of the side length x. So this distance x is the fencing, and this length x is the side of fencing, side of field, and this length here represents the fencing. I think it's important to label the graph because it's very confusing what this vertical side represents here on the graph. It's very tempting to think that it is y because your calculator will call it y, but you're graphing this function, fencing, as a function of x. So let's go ahead and put that, well, first let's decide some values on these axes. So 10 and 20 seem like they are reasonable guesses for this side length x. They give us dimensions that would be good to work with, 20 units for x and 10 units for y, or 10 units for x and 20 units for y. So basically it's a good idea to kind of double your guesses here. So 20 doubled is 40. I'm going to go ahead and put in 50. And for the fencing, I know that I'm looking for something that is smaller than these because I'm looking for a minimum, but it's nice to see a bit more, so I'm going to put my fencing maximum up at 100. Alright, so I'm going to try and graph that and hope for the best. So we'll go to y equals and put in the function 3x plus 432 divided by x. Then we need to set our window like we just had there, 0 to 50, and we'll scale that by 5s, and 0 to 100, and we'll scale that by 20s. And so there is the minimum. Might look better if we had made this 200 instead of 100, but it would have worked fine the other way as well. Okay, so now we want to know what this point is, the minimum. So we do second, calculate minimum, and then we have to make sure that we are on the left side of the minimum and move somewhere past the minimum to the right, and then move it close for the guess, and don't forget to press enter one more time and you'll see the minimum is 12 and 72. Now sometimes your calculator will display 11.9999 or 12.001, but you can tell even in that case that it's trying to be 12 and you can just trust it. So let's go back to our picture here, and I'm going to change this to a 200 and then just sketch in the graph that I saw. I'm not going to worry about accuracy too much, but I know this point here is 12, 72, which represents x, fencing. And so my answer to the question so far, it says what is the minimum length of fencing he will need? So the minimum fencing is 72 feet. And the dimensions of the field are x by y. X we know is 12, and y is 216 divided by 12, which comes out to be 18. Is that right? Yes, 18. So 12 by 18 feet.